I would like to welcome you to webinar 3 in the Net Zero Industries series webinar of Industry Insights. Today's topic is going to be innovations to decarbonise the steel industry. We have a very exciting agenda and some incredibly talented and respected members giving presentations today, including a number of winners of the Net Zero Industry Awards for exciting projects in decarbonising steel. If I could please first, my name is Alan Monaghan, I'm our mission coordinator, but I'd have the pleasure of introducing Elvira Lutter. Elvira is the mission director, in fact the founding mission director of the Net Zero Industries mission, which was launched in 2022. If we could just mute our mics just for a moment, please. Since 2011, Elvira has been the Program and Research Manager at the Austrian Federal Government's Climate and Energy Fund, responsible for the strategic direction and management of the New Energy 2020 Research Funding Program. It's been my pleasure to be working with Elvira for the last 3 years. Elvira, please, if you could give your introduction.
Yeah, thank you very much, Alan. Dear ladies and gentlemen, it's a great pleasure to welcome you at today's webinar, Innovations to Decarbonise the Steel Industry of the Net Zero Industry Mission. In this mission, we are addressing one of the most pressing challenges of our time, the decarbonization of energy-intensive industries. And these industries, you all know, they account for approximately 1/4 of the global greenhouse gas emissions, are essential to achieving the Paris climate targets, and yet energy-intensive industry represents the most expensive and complex sectors to decarbonize. And also challenges that many low-carbon technologies needed for this transformation are still not available at a commercial scale. And there is related to these energies also a very high risk in demonstration. And the webinar is part of the Industry Insight webinar series hosted by our mission. The goal is to transfer deeper knowledge and share experience to help master this challenge. And we address both technical and non-technical issues. We aim to broadcast learning from various countries and industries. And here I would like to thank all the speakers for the time to do the presentation today. And one major aim is to foster collaboration for innovation in this field of industrial decarbonization. The topics of this series range from technology pathways to sector-specific focuses like today, as well as country-specific insights. And yes, the aim is to have around 6 webinars each year, and this is the first one of 2025. And it supports the ambitious goals of the Net Zero Industry Mission. Our aim is by 2030 that at least 50 large-scale demonstration projects are to be implemented with the financial support of our member countries. And the aim is to showcase these large-scale demonstration projects. Then the mission is committed to driving the development of breakthrough low-emission technologies up to technology readiness levels 8 to be demonstrated after 2030. And thanks to the research and innovation efforts of our members, the aim is to decrease the investment costs for these innovative technologies by more than 15%. We all know this journey will not be easy, but through innovation and collaboration, we can achieve these targets faster than expected, and we can also lower the risk. And now I want to thank you for joining us today, and I look forward to the valuable insights that will emerge from this webinar. Thank you very much.
Thank you, Elvira. If I could, please, we'll jump straight to our first keynote presentation. It is my pleasure to introduce you to Andrew Purvis, Director of the Worldsteel Association. Andy is Director of Sustainable Manufacturing at Worldsteel Association. He has over 30 years of experience in the British, Dutch and Australian steel industries. His work focuses on safety, environmental performance, sustainability and greenhouse gas abatement. He's a chartered engineer with a degree in electronic and electrical engineering from the University of Leeds, and he has an MBA from Warwick University. He leads programs at Worldsteel that effectively advance the sustainable practices within the global steel sector. It's my pleasure. Andy, over to you.
Thank you very much. I trust you can see my screen at this point, right? Excellent. Okay. Good day, everybody. I'm Andy Purvis from Worldsteel, and I'm excited to spend a few minutes with you this morning talking about this challenging but exciting transition that the steel industry is looking at. I'm going to crack straight on. And look, I think it's important to understand the contribution of the steel industry. We are a significant emitter, and there is a very clear correlation between production from the steel industry and global emissions, because fundamentally steel makes the modern world possible, and everything that we use is made of or made with steel. So there's a very strong correlation between steel use, energy use, and the reality is, at the moment, every ton of steel we make using the blast furnace process, which is the most significant, represents about 70% of global production, produces around about 2.3 tons of CO2. There are other steelmaking processes that are used. The EAF process uses recycled steel, is a lot lower, and the sort of DRI, direct reduced iron EAF process, is somewhere in the middle that uses natural gas. But the main steelmaking process route is generating around about 2 and a bit tons of CO2 per ton of steel produced, which is a huge challenge. If we look at our contribution to global anthropogenic emissions, the steel industry, depending on how you do the accounting, represents probably around about 8% of global emissions. So we make modern society possible, but we are making a contribution to global greenhouse gas emissions that we really need to address. The challenge, of course, is that as we make society possible, as we make renewable energy and the low carbon future possible, we expect that production and consumption of steel will continue to increase going forward. This data is from, I think, Wood Mackenzie from a couple of years ago, but you see there's a significant increase expected between where we are now in 2025, producing around about 2 billion tons a year, through to 2050, where we could be up to 2.2 billion tons, or potentially even more. This is the challenge we've got, because you need to put that against the expectations which have been given to the industry for reduction. No matter which scenario you look at, whether it's the more ambitious IEA net zero scenario or the sustainable Paris-aligned sustainable development scenario, we see a significant reduction both in steel CO2 intensity and absolute emissions between now and 2050. But we need to set that up against a demand increase. So you see the gap there. That's the challenge. We need to significantly reduce our emissions as an industry, and at the same time continue to make the metal, the material available that society is going to need to transition. This is it's going to be difficult. And if you look, this is some work done by Worldsteel Dynamics, which isn't part of Worldsteel. It has a very similar name, looking at where steel industry reductions are likely to take place between now and 2040. The lion's share is happening in China, but you see almost all regions, you see a reduction. The exceptions would be other Asia, which is largely the ASEAN countries, and India, where we expect to see an increase. Interestingly, of these, the only area where we see an increase in production and a reduction in emissions is in the old NAFTA, the USMCA area. So the message here, I think, is all regions are going to play a role. India will increase, but at the same time, India are looking to increase their production significantly. So they have, I think, a unique set of challenges that they need to deal with. So what is the answer to this challenge? I think the answer is radical change to our industry, and particularly change to the way we make iron, transitioning from the traditional blast furnace increasingly to something that looks very, very different. So I talked about the IEA scenarios and our approach, I showed you the gap, the difficult, tricky challenge between the production that will be required by society and the expectations of our industry in terms of reducing our emissions. The way we see it at Worldsteel, we see kind of three phases to our mitigation strategy, and I would just want to run through those fairly quickly in the remainder of my presentation. It's going to be around efficiency, certainly in the short term. I think the IEA and others agree that if material and energy efficiency are critical. Medium term, we'll see benefits from scrap availability, but longer term, we really need to make those changes, particularly to the way we make iron. And I just want to step you through these three phases. The first is around efficiency, and I think it's incumbent on us and all steel makers right now to make sure that every ton of steel that we do produce is produced with a minimum environmental and greenhouse gas impact. At Worldsteel, we have a great deal of data which we collect from our members, and we've been able to analyze and really try and understand, what's the difference between the best operators in a particular class and kind of the rest of the cohort. And it comes down, we believe, to four key areas. The biggest is raw materials and making the correct raw material selection. Beyond that, we have energy efficiency, process yield, and process reliability, all playing a significant role. And these are the key four levers that make the difference and that form the heart of our step up efficiency program. This has helped us understand the production potential between the top 15% or so and the rest of the cohort. And you can see here some of the numbers. In the integrated area, blast furnace route, we believe there's percentage reductions of around about, on average, 0.3 tons of CO2 per ton of raw steel from energy, around about the same from raw materials, and you see the others, yield and injection rate. In the EAF, it's really about energy and yield as well, not the raw materials in most cases, is either DRI or scrap. So there are benefits that can be gained in the short term, and I think it's, as I said, it's incumbent on all of us to really focus on achieving this. Second step is around scrap usage. We already use scrap within the steel industry. Every ton of steel is recycled, and this varies from up to 100% in the electric arc route to, being between 10, 15, maybe as up as far as 20% in the basic oxygen steel making route. The problem with scrap use is the scrap available to us is a function of two things. One is past production, and the second is the lifetime of a steel product. The good news is, from around the year 2000, and you see on the left, there was a huge uptick in production, particularly in China. And given the average life of a steel product is around 40 years, and this varies depending on the application, this millennial steel is going to get to the end of its first lifespan. Its first lifetime within the next 10, 20 years. So we expect to see a significant increase in end-of-life scrap availability. It was probably around 400 million tons now, and this could go up to closer to 1 billion tons, 900 million tons by 2050. This is really going to help, because every ton of steel that we can do this way, we can use scrap, will make a big impact and reduce the need to reduce new iron ore into iron and steel. Unfortunately, there's not going to be enough of it. As I say, this is a function of past production, and going forward, we expect, for all the reasons I talked about, demand to increase. Therefore, we need to do something else. But EAFs will grow. In advanced economies, they're currently around 40%. We expect, or rather, Worldsteel Dynamics expect by 2040, there could be up to 70%. We also see growth in China. Bit of a reduction in the rest of the world as other countries suck up the scrap, which is currently being exported, and use them themselves. But we expect to see an increase. So by 2040, we might see scrap EAF production going up from around 30% to closer to 40%. We need radical change, though, and we need to change the way we reduce iron over the long term. And I think there's a number of ways we could do this, and I want to step through some of these: hybrid technology, hydrometallurgy using hydrogen, CCS, and there's also electrolysis. I call this electrolysis plus because there's other technologies like the Helios cycle that you'll hear about today that fit into that box. I'll run quickly through these. Hybrid technology is around taking traditional iron making and steel making technology and looking at what we can do using new energy sources and transitional solutions. So in Japan, for example, they've been looking at using hydrogen within the blast furnace. This has enabled them to reduce emissions by around about 33%. And in other parts of the world, companies are looking at substituting pulverized coal with biochar, which again can lead to significant emission reductions. This can be done if the materials are available relatively quickly using existing equipment. Second is an example of DRI. This is in China. HBIS, a Worldsteel member, now have built the world's first, it's a 1.2 million ton scale hydrogen steelmaking DRI plant. It's successfully delivered its first products. This can use hydrogen from the coke ovens in the short term and transition to green or low carbon hydrogen when this is available. This is running now and the company are learning. CCS has been in operation in the UAE since about 2016 at Emirates Steel, Arcan, now M Steel. So this facility is capable of capturing up to 800 million tons of CO2 per year, with an expectation in phase 2 this will increase significantly going forward. So this has taught us a lot, I think, about using CCS, particularly on the direct reused iron route, which potentially is an easier application for this technology. Baogang in China expect to commission the world's first blast furnace CCS project this year, likely to come on stream in 2025 rather than 2024 in what it says there. 500 million ton facility applied to the blast furnace stoves and lime kiln. This is very exciting. I think we're all looking forward to seeing this happening. ArcelorMittal, I will not dwell on steel and all because you're going to hear about it in great detail from our colleague Wim, who is on the call. But this again is a very exciting demonstration project showing the capability of CCUS within the iron and steel sector. And finally, there are companies using low carbon feedstock. Aço Verde de Brazil are using sustainably produced charcoal to produce iron with a footprint of 0.06 tons per ton rather than 2.3 tons per ton, which we see in conventional production. And other steel companies are also using biomass. I see the time is ticking by. I will push on quickly. In terms of where projects are happening, I think the message here is, I think Europe's leading the way in terms of the number of projects, but we are seeing important developments right around the world. Particularly, I want to look at China, as China is such an important player in terms of global steelmaking, producing around about half of current global production. My final message really is that there isn't one pathway. There's different starting points, though it's not as if there is one solution that will be applicable to all technologies, all steel plants around the world. Companies need to look at where they are, and this includes looking at their assets, their inputs, what they're using in terms of raw materials and production, the environment they're operating in, and the IP that is available to them. To close out, I think there's a number of the technologies there. We can use it. There's a bit of development that needs to be done. The key now needs to be really on demonstration and deployment. There are certainly some challenges that remain around technology, and technology challenges probably include the technology readiness of some of these technologies, focusing on efficiency, the availability of infrastructure to provide hydrogen and CO2 and renewable energy, raw materials. Looking at the economics, there's still issues over cost and funding and whether steel companies taking these new approaches can be competitive. And also, we're seeing the potential emergence of a new industry producing green iron or low carbon HBI in some regions and shipping that rather than shipping ore. Policy support is going to be important, and that international coordination and collaboration piece between countries is important. Also, we believe at Worldsteel there's a huge gain to be had in terms of standardizing methodologies, which we use for measurement of carbon footprint and reporting. And finally, in the social economic side, there's going to be an impact on workforce. We're seeing that among first movers and companies that are changing the skills that we will need. Stakeholder engagement is going to remain to be very important. We need to talk to our workforce and our communities who are going to be affected by these changes, and just maintaining, I think, that focus on life cycle emissions and understanding the real impact of projects on our industry. I'll finish there. So to conclude, there's going to be a transformation, I think, over the coming decades to the manufacture of iron and steel. We're going to look at efficiency, scrap use, and ultimately we will need breakthrough technology to make this change. Hybrid technologies are going to ease the transition, and we are starting to see demonstration at industrial scale from first movers. To do this successfully, we can't do it alone. We require collaboration across our ecosystem. And the key areas are probably technology, economics, policy, but also those social dimensions. And Alan, I will probably finish there, just in time, I think. Thank you.
It is perfectly on time. Thank you, Andy. Just a reminder to all of our subscribers here, if you have the opportunity, or rather the inclination, we can ask questions in the Q&A field of Teams. We'll filter those through and ask them if we have time to each speaker. I will kick off with one question, though, for you, Andy. Hydrogen. What kind of central role is this going to be playing, though? The dependence on steel on hydrogen, to me, seems pivotal. What's your views?
Look, I think hydrogen is going to be important. And, I sit in Europe, and I think for those who sit here, you might be looking at our industry and thinking hydrogen is the solution. But, as the steel industry is bigger than that. And I think if we look around the world, there's going to be a plethora of different technology solutions that we are going to need. I absolutely think hydrogen is going to play a role. We are going to have the technology available to us. One of the issues is going to be the availability, I think, of hydrogen. Can we source sufficient hydrogen for the projects that people have in mind now? Is there going to be enough low carbon energy to make it? Do we understand how to store it and how to manage it? So it's going to play a role. It's not the only role. We will need all the other things, including, I think, CCS. And between regions, I think it'll vary. It's clear Europe has sort of bet the farm on hydrogen. I think Australia have taken a similar approach with the way they see their steel making developing. But if you look at other regions, China, Middle East, and India are particularly key, and Southeast Asia, I think technologies like CCS are also likely to play a significant role.
Excellent. Thank you for that. No other questions have come through. Please, if you do have a question for Andy, we will be able to hopefully have time at the end to circle back. But with that absence of more questions, if I could introduce our next speaker, please. It's my absolute pleasure, given he's a good friend of mine, Jeffrey Brooks. Professor Jeffrey Brooks is a professor at the School of Engineering at Swinburne University in Australia. He currently coordinates this is going to seem rather strange for you, the research for extraterrestrial processing at the university. And of course, he is the program leader in the ARC program for the Steel Innovation Hub. He has published over 250 papers on fundamental aspects of steelmaking, aluminium production, and materials processing in general. Professor Brooks is a fellow of the Institute of Materials, Minerals and Mining for the UK, and won the prestigious Bessemer Medal in 2023. Jeffrey, please share your screen and over to you.
Sure, thank you. Thank you. It's nice to be here. Yeah, no, that's true. I'm looking into how to make metals on the moon. Yes, that's one of my interests. But today we're going to be concentrating on the Earth, and we can have another discussion about how to make things on the moon. Let me just get this talk going here. So basically, unfortunately, it's covering there's the vital thing I'm looking for. All right, so you can see my slides now?
We can.
Great. All right, Andrew did a wonderful job getting a lot of the basic information, which means that I could cut out quite a few slides. So I'm pleased about that. You did an excellent job. I'm going to give you a talk about innovation and probably concentrating a bit more on the metallurgy rather than the overall economics. One thing I would say is that
I've lost everything at this point. Am I alone? I can see you moving, Alan, but I've lost Jeff. You're muted.
I think it is. I think it is just Jeff that's frozen.
Yeah, that's true.
It's rather unfortunate timing.
Time to improvise, Alan.
Well, if we could, before you go, Andy, there's a question that while we're waiting for Jeff to come back.
I was typing an answer to that actually. So yeah, I'll fill in slowly. Well, hopefully Jeff comes back. No, it's a good question. It was about really, I think, why, while in most areas we see the use of the EAF increasing as we go forward, which makes sense with the story I told about more scrap being available, set against the sort of other regions, there was a reduction, and why that might be the case. I think the reason probably is right now, many countries are exporting scrap. For example, there's a significant scrap flow from the UK to countries like Turkey and from the EU to India. I think as we go forward, countries are going to look more at their own emissions and think, well, actually, I could use this. I could use this scrap myself and cut down on exports. So if you're currently sitting in a country that is pulling in scrap, like Turkey, just as an example, you might find that the scrap that historically that you're relying on and using is not available to you anymore, especially with increasing production. If you're going to maintain access to iron and steel, you have to look at other routes to make it. So I suspect that's the trend that is underlying that change. The scrap has been sucked into countries who are using it to meet their own climate goals, and countries outside who previously have imported that scrap, it's no longer available to them. So they're going to have to reduce their reliance on EAFs and get their iron from somewhere else.
Excellent. Thank you for that, Andy. I can't see that Jeff has come back. He's dropped off the call. He's having obviously network issues. In the spirit of the show must go on, Cecily, are you actually able to share your screen and we'll jump to you as the next speaker?
Yes, sure. I will share my screen.
Excellent. I'll just do your introduction. It's our pleasure to introduce Cecily Sigano. With over 20 years experience in the the energy and industry sector, Cecily currently works for the OECD in the Clean Energy Finance and Investment Mobilisation Program, which focuses on industry decarbonisation financing. Prior to joining the OECD, Cecily held management and project management positions in a worldwide energy company, as well as consultancies on energy transition. She holds a Master of Arts in Political Sciences, both energy and environment, and both engineering and Master of Science degrees. It's our pleasure to introduce Cecily. Please.
Thank you very much. And can you see my slide?
We can see your slides. Yes.
Yeah. Okay. Perfect. Yeah, good morning and good afternoon to all of you, and a warm greeting also from my side, and thank you very much for the invitation. So pleasure to join the conversation, and I'm very pleased to share insight of some of our programs that we are conducting at the OECD indeed on that topic. And more specifically, I will touch on the financing aspect that relate to the decarbonization in emerging and developing economies. So let me start by briefly introducing the broader program in which we operate, so the Clean Energy Finance and Investment Mobilization Program, which is an OECD program funded by a group of countries, implemented in several emerging and developing economies, and with the objective to help to accelerate the clean energy finance and investment by strengthening the domestic enabling condition, and including for the industry sector and including for the steel sector in that context. And so because industry decarbonization is crucial, we have developed a specific framework to support these emerging and developing economies on industry decarbonization, and with the objective to provide recommendations to government on what are the financing solutions, what are the policies and regulations that can help to accelerate industry decarbonization in a specific country for a specific industrial subsector. And we are currently implementing this framework in several countries, and including for the iron and steel sector. So I will share some insight and outcomes from these different programs. So as a brief introduction, it has already been recalled, but just to say that decarbonizing the iron and steel sector is indeed key to reach climate goals, as the sector accounts for around 8% of the global emissions from the energy sector. But it's not just a matter of scale in terms of emissions, it's also a matter of scale in terms of investment, because we know that massive investments are needed, and given the scale of this challenge, we will need to mobilize all sources of finance, whether international, domestic, public, and private. And for emerging and developing economies, the challenge is even more pronounced because manufacturing industry capacity is growing and is expecting to continue growing for economic development, and at the same time should decarbonize. So still decarbonization is crucial, but still decarbonization faces implementation challenges, and we have clearly indeed a gap between the decarbonization ambition and the implementation on the ground, which is underpinned by also lack of viable business cases for net zero aligned projects. So we have, for instance, on the one hand, almost all crude steel production, which is located in countries that have announced a net zero target for their whole economy. But when we look at the level of the steel company, then this share is significantly lower. And if we go one step further and look at what is the actual primary steel production, which is compatible with a net zero pathway, it's even much more lower. So increasing investment flows is necessary, but we also need to ensure that these investments will target and are targeting projects that are compatible with the net zero trajectory. And when we look at the commercial projects that are planned or underway in the coming years, we have a significant share of planned steel capacity, which relates to the higher emission intensive production routes, so namely the blast furnace routes, and especially in emerging and developing economies, especially in Asia, and which means that there is a strong risk of emission lock-in and stranded assets. So we have a lack of deep decarbonization project pipeline, and these projects indeed are seen as risky. And there are multiple challenges which increase the risk profile of this type of project. And here I mention a few examples of the challenges. So of course, technology aspects with breakthrough technologies that are needed at scale, but currently with low commercial maturity. Competitiveness challenge, of course, where the implementation of low carbon technologies imply a higher cost of production, and this competitiveness aspect is particularly at stake as steel is global commodity, highly traded and facing fierce competition. There are also broader systemic challenges that are not necessarily directly linked to the steel sector itself, but that are critical enabler for the decarbonization of the sector. For instance, I'm thinking about the low carbon infrastructure or the broader policy framework. Challenge, of course, about the scale of investment needed for transforming a single facility. We were talking about billion euro, not million. So high capital intensity, high upfront cost. And last but not least, market challenges referring, for instance, to offtake risk and the need for a common understanding and definition of what is green steel. And these barriers, I would say, are even more pronounced for emerging and developing economies. For instance, because of lower regulatory and policy uncertainty, because of a lack of access to innovative technologies, limited access to capital in some cases, high cost of capital, or also limited availability of low carbon infrastructure. So challenge even more pronounced for this country. So we have multiple challenges, but also multiple economic de-risking and financial instruments that are available and which can help to attract investments in low carbon steel projects. And it is precisely the combination of instruments that could help to alleviate these type of barriers, depending on the challenge to be addressed, but also, I would say, depending on the stage of the project. So we have analyzed different type of instrument mechanism that could help to support, to alleviate this barrier. And we have a wide range of instruments. So for instance, some instrument would be better placed to address high upfront cost, such as concessional loans, tax rebate. Other instrument would be better placed to address the cost of capital, for instance, sustainability linked instrument. And some instrument would, for instance, address operating cost or support, revenues, lower the risk of revenue uncertainty, such as, for instance, carbon for difference or offtake agreements. These are some examples, but just to say that there are multiple instruments that can help to support this type of project and attract financing in this type of project. We have also extensively conducted case studies on this aspect, financing instrument, enabling condition that can help to support a low carbon project. And we draw some key learnings on what could be successful approaches. So one key learning, for instance, in terms of financing instrument characteristic, as mentioned, we see that the combination of multiple instruments and the use of de-risked instrument is really key to support this type of project. Also, direct public support can be used for targeted and time-bound uses. In terms of enabling condition, we saw the importance, for instance, of sustainable taxonomies, and for emerging and developing economies, also the importance of capacity building to improve institutional readiness and the maturity of the domestic industry. In terms of replicability and scale-up, we've seen that innovative financial instruments at very early stage are key to support low carbon project, and the crucial and very important aspect of having project pipeline to really scale up and ensure this replicability. In terms of governments and implementation, the key aspect of multi-stakeholder approach, which is key to support this project. And again, for emerging and developing economies, very important aspect of knowledge sharing and matchmaking platform to better and rapid implementation of such low carbon projects. So for the case of emerging and developing economies, I'd like now to share some insights from a recent work and recent report on the financial and technical assistance for industry decarbonization in emerging and developing economies. So we have prepared this analysis for the Climate Club, which is a high-level intergovernmental forum focusing on industry decarbonization. And we have looked at the financial and technical assistance, which has the potential to support emerging and developing economies, precisely in developing the enabling condition for industry decarbonization and to help to catalyze, mobilize private capital. So we look at heavy industry sector, including the steel sector, to see to what extent financial and technical assistance has been provided to support industry decarbonization, including for the steel industry in particular, in these emerging and developing economies. And so I share some insights of critical and key message. First one is that the first key message of the report is that overall the financial and technical assistance for industry decarbonization, including for the steel sector, has not received the necessary attention so far. So here is an illustration precisely of the public, bilateral and multilateral development finance that has been provided to the steel sector. So for instance, for the steel sector, we saw that the sector represented only around $0.6 billion of the mitigation-related public, bilateral and multilateral development finance over the past 20 years. So this is the amount that has been provided over the past 20 years when we look at the mitigation-related public, bilateral and multilateral development finance. And I would say that beyond this amount itself, so which is very low when we see that it's for the past 20 years, what is important to note is that the steel sector actually represented much more less than 1% of the total recorded mitigation related development finance. So meaning that in the steel sector, when we look at the total development finance that has the objective of mitigation, reducing emission, the steel sector will represent a very small share, and this despite its significant share in terms of emission. Other interesting aspect to look at is that if we look at the development finance that has been provided for the steel sector over the past 20 years, only half of these flows are actually directed toward mitigation, decarbonization purposes, which means that even when focusing on the development finance directed to the steel sector, there is room to further target this flow towards decarbonization purpose and emission reduction purpose. If we now look at the characteristic of this financial flow that has been provided, so beyond the amount that I've just mentioned, interesting to see also that they are characterized by the very limited pool of country provider, country recipient, and financial instrument, which means that there are also opportunities for the steel sector to potentially benefit from dozens of providers that have been, for instance, recorded for other sectors, beyond industry sector too, and also steel sector which could benefit from a wider variety of instruments, because here, for instance, what has been provided over the past 20 years, we see that almost all the support has been provided only by one provider. Almost all the support was directed only to two countries and only through debt instruments. So there is very low diversification that we observed. And on the type of project themselves, also interesting to see which type of project have benefited from this bilateral and multilateral support. We see that these are mostly projects focusing on energy efficiency, waste management, circularity, research capacity building, meaning that these are not directed towards deep decarbonization project and implementation project too. So, and it was indeed confirmed when discussing with international financial institutions, IFIs, that industry decarbonization based on breakthrough technology are really a nascent space. And so this is indeed, so far, was not really targeted. Precisely, if we look at now a different view, if we look at the climate funds and program, IFI's program, that are currently exist, we look at to what extent these existing funds and program can cover the decarbonization of the industry sector and can cover so the decarbonization of the steel industry. So we look at what are the existing channels of fund and IFI program which could cover this. And actually we see that there are various funds which could support industry decarbonization projects in general for emerging and developing economies, but these funds do not cover the industry sector in the same way. We have actually most of these climate funds that can cover the industry sector that are very transverse funds, namely they are not sectoral specific. For instance, these funds are associated to an overall purpose of supporting climate goals or sustainable development. And so industry decarbonization project and steel decarbonization project could fit into these funds, but the scope coverage is by nature much more wider. So that's the most of the funds that are available today are transverse funds. And there are very, very few funds which actually are very narrowed to some sectoral approach, which include the industry sector. And this could be a barrier because especially when we consider this transverse fund, because it means that industry-related projects, in that case, may have to compete with projects of a very different nature, for instance, on transport, land use, or energy access. So very different type of project that compete to access to these funds. And given the specific challenge and multiple challenge on financing industry decarbonization project, in particular for emission-intensive subsectors such as steel, it means, the business case for such project could be of disadvantage, of course, comparing to those of other sectors. However, in what we found also is that there are some good news because international financial institutions and funds that we interviewed and surveyed acknowledge that there is a growing interest in developing specific funds and programs towards industry decarbonization. There are emerging programs that are coming supporting specific industry decarbonization projects. And of course, when we discussed about what are the main barriers they were facing and what could be the main instrument and solution to support, the lack of project pipeline and market risk appeared as the most critical barriers towards developing such projects in emerging and developing economies. And instruments such as debt and concessional finance, but also, blended finance example, for instance, they were reported as the most relevant instrument and scheme to support such project. And of course, de-risking instrument, very important tool to support this type of project. And they mentioned specifically through guarantee. But just to say that there is a growing interest in developing new funds, and industry decarbonization appears as indeed a new topic in this fair. To conclude on this topic of financial and technical assistance, so based on the key findings, we raised 6 key areas for action. So to conclude, there is a need indeed to focus on industry decarbonization, including steel, when it comes to financial and technical assistance for emerging and developing economies. So we need more in a more diversified way and also in a more targeted way. So based on the key insight that we've learned. And I would conclude by saying that overall, these key areas for action are also an opportunity actually to boost international cooperation and partnership for financial and technical assistance for industry decarbonization. And that could benefit also to innovation, of course. And in terms of international cooperation, precisely, following this report and this discussion on financial and technical assistance, it's worth noting that there was a call for action that has been launched at COP29 with a global pledge to scaling international assistance for industry decarbonization. So where government from, for instance, Germany, UK, Canada, and the climate investment funds announced to partner to scale international assistance for the decarbonization of industry in developing market and emerging economies. So which is designed to mobilize and catalyze investment from the private sector. So opportunity to boost this cooperation. I will stop here and thank you very much for your attention. I'm happy to follow up on question. Thank you.
Excellent. Thank you, Cecily. I'll forego my question that I'd mooted, and I'll jump to one from the audience, please. What actions? It's from Elliot Marty. What actions can be taken to avoid the planned deployment of new BF-BOF capacities in Asia?
Yes, actually, I would say that relates to a broader question also on how government. What could be the role of government to support the steel decarbonization? There is a role, I would say, to play first in providing, of course, the enabling condition to make this investment happen in new low carbon technology and move away from emission intensive technology. And it starts by giving indeed clear signals to the industry and investor on decarbonization target, for instance, providing a long-term vision and certainty on the policy and regulatory framework to support this decarbonization ambition. This is very important. So this includes, of course, development of a wide range of policies and support, both from the supply side, for instance, by supporting innovation demonstration project, as we're talking about innovation, developing also sustainable finance taxonomies, for instance, which is very important to channel the investment towards a low carbon project, pricing emission, of course. So there's a wide range of policy from the supply side, but also from the demand side, because by supporting the development of lead market, for instance, through green public procurement or developing regulation and standard to define what are green steel products, that could really be a strong catalyzer and support to develop such low carbon project and move away from emission intensive projects. So everything that can give clarity and increase confidence in investment for such low carbon project would be key. And the second key aspect, I would say, is really about risk sharing to ensure that this low carbon project can be developed. So here government, when we talk about risk sharing, that can enable viable business plan for developing such project, for instance, by providing the risking mechanism, as I was mentioning, tax credit or CCFD, but also by supporting new form of financing approaches. And so this is very important with concessional loan guarantees, capex grant or green bonds. So everything that could help to de-risk investment in low carbon technologies, low carbon projects. And I would also say that, public-private partnership will be also key to mitigate this risk for investment for this low carbon project, especially when we think about low carbon infrastructure where, in that case, economy of scale matter.
Excellent. Thank you so much for that. I think that actually also addresses a lot of the intent of the next question I was going to go to, so I might skip over that. If I can, one question was, would the report be downloadable? And we can see the link is already in the chat for those who'd like to access the report from the Climate Club. So thank you very much, Cecily. I'm told reliably that Jeff Brooks has managed to get his internet problem sorted. And
thank you very much, Cicely, for filling in so quickly. I'm very sorry about that.
I won't do your introduction again, but if you'd love to share your slides and jump straight in, thank you, Cicely, and welcome, Jeff.
Thank you. All right. Well, I need to get into share screen first. Wait a sec. All right, share screen. And let's hope for a bit of luck. Right, my screen. And I need to move this again. This is the bit that's crucial. That's it. Let's go. All right, can we see the screen?
We can. Excellent.
Great. So let's as was explained very well by Andrew, there is the issue of that the main cause of carbon CO2 is the iron making step. So for those who aren't familiar, you have to make iron before you make steel, basically. And the iron that you make tends to have impurities in it, which then have to be purified in the steel making step. Now it's more complicated than that, but that's the essence of it. When we look at current iron making technology, it's dominated by the first reaction, which is iron oxide plus carbon with some flux. So this is material to help melt some of the slag materials. And you end up making an iron, which is liquid. You make some slag and you make carbon monoxide and carbon dioxide. And that's currently roughly about 90 to 95% of the world's iron making at the moment. The other way we make iron at the moment is the second way, where you get natural gas. And the natural gas at high temperature basically decomposes into hydrogen and CO. And it reacts with the iron oxide, forms iron, forms water, and forms CO2. All right, so that's currently, something close to about 10% of the world's iron is made that way. Another way that you can make iron is with hydrogen. So you can use hydrogen to take away the oxygen to produce water. Now, this technique is scientifically proven, and it actually has been also done at commercial scale. It's important to know that a commercial scale plant based on that principle has operated already some 20 years ago. So we know that can be done. The question is, can we do it at scale and economically? Another way is to use electrons, which is basically electrochemistry. So basically use electrons to break down the iron and produce oxygen. This is currently at lab scale. We have done it. We know you can do it. We know how to do it, but it's currently being tested at lab scale. Another interesting technique, which is going to be talked about tonight, is using a reactive metal. So you find a metal that loves oxygen more than iron, and there's a number of them, and you react it with the iron oxide and you form iron and a new oxide with the reactive metal. This technique is used to already make magnesium titanium in the world, but it's not currently used to make iron. It's currently been studied at a lab scale by our friends at Helios, and they'll be talking later tonight. Just so you know, the reactive metal they're using is sodium. As you can imagine, the economic success of that approach will depend an awful lot about how much sodium you lose in the process, how easy it is to recover the sodium, for example. So at the moment, the basic plan is that we're going to phase out the first two into the final three. So basically what we're hoping to do is, with time, phase out the use of carbon and natural gas and bring in hydrogen, electrons, or reactive metal. These are the major choices. Another approach that people have is to say, well, let's try and replace the carbon and natural gas with something that's more sustainable, like a biomass. All right. So basically, you're doing the reactions of 1 and partly 3 by using biomass. So you're saying, all right, well, a biomass, if we can grow trees to match the use of the biomass, for example, then we could claim neutrality. So that's another approach. And the other approach was also mentioned by Andrew, which is basically using some carbon capture and storage technology to capture the gases from the first two processes. So instead of building 3, 4, and 5, using carbon capture, and Andrew mentioned there's some testing going of that in both the Middle East and China. So these are the basic approaches, I think summed up in one slide. So I've been a little bit ambitious to try and explain such a complex thing on one slide, but that's basically it. Now, when you look at who's making steel, as you'd be aware, it's dominated by China. And India is second, and it's quickly rising. It's a developing country. It's building a lot of infrastructure, and you'll see it rise. When you look down the list, you'll see that Australia doesn't really emerge on that list because it's so small. We have a very small steel industry. And you can also see that European steelmakers, though large industries, are relatively small compared to China and India. And I suppose that what that brings up is that really these changes need to occur on a global level, particularly in China and India, if they're going to have impact. When we get to the supply side, particularly the iron ore, Australia is a very big player. So Australia dominates exporting iron ore, the iron ore that you export around the world. And some of our big competitors are Brazil, for example, and South Africa and Canada. But Australia really does dominate iron ore export. And the way that Australian iron ore can be utilised in these new processes is a crucial issue. And that's one of the things that keeps my research very busy at the moment, is trying to deal with this issue about how iron ore is produced in Australia will go in these new processes. Just a little bit about iron ore. Iron ore really comes in 3 or 4 major sorts of forms: hematite, magnetite, siderite, and goethite. Most of the Australian iron ores that we're currently exporting are the hematite, goethite combined. The magnetite has the very special quality that it is magnetic, as the name implies. And this means that you can enrich magnetite relatively easily compared to some hematites. At the moment, the amount of high-grade ore, which we could classify as being above 65% iron, is really a relatively small part of the world's supply. It's probably well below 10%. The lower grade ores, probably between about 58 to 62, for example, they are plentiful. And those sort of ores have lots of gangue materials in them. And they also have other elements like phosphorus that can be causing problems in the processing. These ores are the kind of ores that Australia is exporting. And most of these ores are being put into blast furnaces, not into DRI processes that use natural gas, for example. And this is something of great concern because we are looking at the potential phase out of the blast furnace. So how will these ores perform in these new processes is a crucial question. We've been doing a lot of research at Swinburne and other universities around Australia. This is from a study that I did with my friends at ANU, funded by the HILT CRC. And this looked at if we got Australian ores and if we put them through a shaft DRI process on the top there, or a fluidized bed, another major DRI process, what would happen if we put that directly into an electric arc furnace? That's the top route. Or if we put it through a process to get rid of all the gangue and then into an oxygen steelmaking vessel, which is already a well-known process. And this is what we judged with the iron ore process as the most likely routes to be for Australian iron ore. What I can tell you is that if you have much more than about 60, if you have an iron ore below about 63%, 64%, the top route where you go directly from either the shaft or the fluidized bed into the EAF is likely not to be viable. It's only going to be viable when you're above, say, 64, 65%. The bottom ores, the bottom route where you put it through a melter or smelter and then into an oxygen steelmaking vessel is probably what will be the most viable approach if you are treating the typical Australian ores. There is another option to appreciate that takes too long to explain in this meeting, but another option is to do very clever things in the mineral processing, this beneficiation step. So this is all about innovation and beneficiation so that we don't have to worry about removing these slag or gangue materials in these other stages. So this is the kind of thing that we're trying to analyze in Australia. And as you can imagine, very hard to summarize in a 15-minute talk, but I want you to at least appreciate it. If you have rich ores, so the first scenario, this top one, where you just go from a DRI process into electric arc furnace, you have the situation they have in Sweden. So in Sweden, they have the happy situation of having relatively cheap renewable energy, and they also have quite rich ores. And this means that they can contemplate a process where you don't need to have a separate stage to remove the slag. And so this is what we're seeing as the flow sheet. I want to emphasize this is unlikely to be a general solution because of the reasons I said before. Basically, if you put an Australian iron ore into this process, the electric arc furnace will not be able to be productive. It'll be producing way too much slag, and you'll basically have problems processing it. So if you're using a typical Australian ore from the Pilbara, for example, you would end up with a very excessive slag generation in that EAF stage. So basically, this is not, I don't think, a general solution. It's more like specific to rich ores, something important to appreciate. So what's really going on with these low-grade ores? What are we doing? On the right-hand side, I have a cross-section of a blast furnace showing the internal structure of a blast furnace. And basically, a blast furnace is a shaft reactor with solids and gas. That's the top part. And down the bottom, it has a lot of molten phases, very hot slag and metal phases being formed. What we're really saying is we're going to do this in a two-stage process. The first stage is a hydrogen, or perhaps some natural gas as well, as Andrew explained, in the DRI process. So that's this shaft here, going into a melting smelting furnace, which is fueled by electricity. So we're basically replacing the blast furnace with these two steps. That's essentially what we're doing to deal with these lower grade ores, the most common ores in the world. I'm involved with a large project that's funded by the HILT-CRC and the various iron ore companies in Australia and some of the steel makers, and we are looking into the details of these electric furnaces and how these furnaces work, how they can be scaled up, how do they operate, how do you manage them so they produce the right products. So this is something that there's a lot of investment in Australia, and many of you might have heard that recently we're going to be building a pilot plant of one of these facilities in Western Australia. And also BlueScope, the Australian steelmaker, already has a current version of this process operating in New Zealand. So you would expect Australian iron ore and steel industry to be leading some sort of innovation in this area over the next period of time. So where's green steel up to? Well, at the moment, it would appear that hydrogen is the most likely route for green steel. And the reason being, it's difficult, I wouldn't say impossible, but difficult to really replace large amounts of coke and coal in the blast furnace. And there's been quite a lot of testing of that, and it's showing that it's going to be very difficult to go beyond 20 to 30% replacement of the coke. That may change, but at the moment it's the current state of knowledge. Some people want to link carbon capture to blast furnaces and DRI processes, but that seems to require to be near a depleted ore well or some very suitable geology, not geometry. And I don't know yet it's been shown to be a completely viable solution as a general solution. Biomass routes, they already exist. There are well-known biomass routes of making iron, but they tend to be quite expensive and difficult to do unless you're close to a very large supply of biomass. So at the moment, the only place that is viable just at the moment is in Brazil. Electrolysis and metal thermic routes are promising. They don't involve hydrogen, so that could be an attraction, but they're a long way from commercialization. So those processes are exciting, and I'm working on at least one of them. But they have, there's a long way to go to commercialize them, basically. The whole hydrogen issue is very important to appreciate. The amount of green hydrogen available in the world at the moment is very low. It's a very small number, and it's nowhere near necessary, the amount necessary that we require to make the volumes of steel that we're after. So that's the scale up of green hydrogen production is a massive issue if we're going to go down hydrogen. I saw a talk recently by Thesis Krupp, and they're currently selling 20 megawatt electrolyzers and trying to scale them up to, say, 200 megawatts. Now, that sounds very large, but that actually is still quite small compared to a steel plant's requirements. Steel plants need gigawatt plants, right? So though green hydrogen is scaling up, it's still quite some way from the scale that's required for good-sized steel plants. The cost of green steel is going to be very sensitive to the cost of hydrogen. You won't be surprised to know. This is some calculations done which show that even at $3 a kilo, which at the moment would be very cheap, you're still adding like 50% to the cost of the steel. So we're talking about a very large, increase in the cost, which is one of the reasons why people are nervous to make that transition. This is current cost. This is some data from Bloomberg. And if you look at this data, it's basically showing that green hydrogen at the moment is selling between $4 and $10 a kilo, roughly speaking. So green hydrogen at the moment is currently quite expensive, and it's one of the reasons why there's nervousness about investing and building straight away. People are waiting to see whether the costs can come down. People are also starting to contemplate other forms of hydrogen, and it was alluded to by Andrew, where people are saying, well, do we need to have pure hydrogen? Can we have off gases that are mixed up with other gases? And there's a whole color chart here of different sorts of hydrogen, each of them with different carbon intensity levels. So I think at the moment there's a bit of a push towards not just saying we have to use green hydrogen. We perhaps need to look at hydrogens that are cheaper to make, and they may not have quite the low CO2 as the green hydrogen. So this is quite a thing of our analysis at the moment. So the challenges for green hydrogen, I just talked them through, but just to summarize them, is there a suitable supply of green energy to build all these green hydrogen plants? There's currently low scale production, so people are nervous about that. And there's concern about cost and supply. Lean ores, how will they perform? Well, there's good reason to believe they will work in these processes, but we need to show that and get confidence in it. And there may be also a reason to look at trying to get away from having to pelletize and whether we can perhaps feed into a fluidized bed. That's another thing that people are looking at, which would take out one of the steps. I am involved with some exciting hydrogen DRI processes. There will be talk later on about this, but just to sort of blow our own trumpet, Swinburne is heavily involved with Calix, and this is their pilot plant, and it's a new type of hydrogen DRI plant, which is used what's called the flash reduction approach, and that will be explained later on. Basically, we've been discovering some very exciting reaction kinetics in these processes. So the scientific aspect of this is really exciting. This is from work at Swinburne with our friends from Calix. And you see these very rapid reactions in this Calix reactor where you're making iron in under a minute. So that's a very exciting part of this scientific part of the work. There's also electrolytic loops, as I alluded to. There are people working at molten oxide electrolysis, salt, and also aqueous. Myself, I'm working on molten oxide electrolysis. And we've recently done published some techno-economic data on molten oxide electrolysis. And this chart shows that in terms of operating costs, that molten oxide electrolysis should be competitive with hydrogen DRI. Now that remains to be proven, of course, but certainly our calculations suggest that. And we published that with all the data as open as possible so people could analyze that. So there's a whole lot of interest in the electrolysis route because it doesn't require hydrogen. There's a lot of scientific challenges with electrolysis routes. One of the big challenges is to find anode materials. This is from a paper published by MIT, who've done a lot of good work in this area, and they're proposing chromium iron alloys as the right anode materials. This still has a long way to go. It's quite open to what would be the right anode materials if we start making iron this way. It's a very interesting area. So the big picture is hydrogen iron making has impetus, particularly in Europe. There's a lot of interest in investment. There's some also significant investment in Australia, I'm happy to tell you. Cost and scale of green hydrogen is a major issue. In terms of these high gang ores, it would appear that these electric smelters are the likely solution. So basically, we can visualize a future where there are hydrogen DRI plants connected to electric smelters. A really big issue is perhaps Australia, instead of exporting ore, should be making the iron in Australia because we have lots of renewable energy. And that's something internally that gets a lot of debate, and there is some investment in that area. I think the future of electrolysis, metallothermic and biomass options, they're all up in the air. It's an open field. And I think basically it's a time for innovation and risk. And I can't tell you, it's a very exciting time to be working in this field. So I hope I haven't overstayed my welcome. So I'm happy to answer any questions.
Excellent. Thank you, Jeff. I do have a question for you straight away, and then one from the audience that we'll jump to very quickly. What do you think is the biggest obstacle? It's very quick answer. What's the biggest obstacle to achieve net zero steel production?
I would love to tell you it's metallurgical science and you need to give me millions of dollars to sort that out. But I think actually it is actually the supply of renewable energy and the cost of producing hydrogen. I think these are the sort of combined big issues. If that we don't overcome that, we may have to try and find answers that don't involve hydrogen, but then we'll still have the renewable energy issue as well we have to sort out.
No worries. There is just one question. It wasn't directed to you, but I think you might be a good person to answer it here. Just scrolling back to find it in the chat. It was asked early on in the presentation. It said, where are we? Sorry. Okay. We saw from the presentations the importance of scrap metal usage.
Mm-hmm.
Could the speakers elaborate what other aspects related to circularity and circular economy are particularly relevant for steel decarbonisation?
Yeah. You are talking to exactly the right person. That's my favorite topic almost. Right, so there are a number of issues. The first issue is, roughly speaking, and I'm talking in rough terms, the amount of steel made in the world compared to the amount of scrap available is about 50%, right? So we don't at the moment have enough scrap to satisfy, so we recycle steel well, but we don't have enough to satisfy demand, right? Now, you could argue that we should bring our economy back to what we're producing to go fully circular, but that would be causing an extraordinary societal and industrial revolution in the world if we did that. But that's the current situation. Now, the other problem is that a lot of the scrap is quite low grade, and the technologies for upgrading scrap are not that advanced. So if we could upgrade our scrap more, we could make higher grade products with our steel, and that would attract more investment in scrap. So I think the two issues are we don't have enough scrap to currently match demand. And secondly, there's an issue of quality. And I think that can be solved, but it will need investment and it will need quite a lot of time in development to be able to get it to the point where people go, oh, we should just use scrap to make everything. Now, I should tell you that the country that's closest to that kind of model of thinking is the US. So the US has invested pretty heavily in scrap processing, and they do make a lot of high grades of steel using scrap. And they have about 70% of their fleet is electric arc furnaces. So Donald Trump, who's here right now, would be boasting about how green they are already. That's what he'd be saying. But certainly there is some truth that they have got some advanced scrap recycling technology, but it's not uniform around the world.
Excellent. Thank you for that, my friend. In the interest of time, because we are running a little bit over, I'll thank you there, Jeff. So if we do get some spare time at the end, we will try to come back for more general questions from the audience. If I could just ask people to remember, please ask your questions in the Q&A field and leave the chat field for just general chat. That'll make it much easier for our admin team to actually find through and filter out those questions for us. If I could now jump to introductions. Our next speaker is also from Australia, Chris Ormston. Chris has over 20 years of experience with metals and minerals processing in technology companies and large-scale heavy industry facilities. As the general manager of Calix's sustainable processing business, Chris leads the development and application of the Calix calciner technology aligned to globally strategic business opportunities to generate revenue streams for Calix across the mineral metals industry. Chris holds a bachelor's degree in engineering and environmental studies and a master's degree in materials, manufacturing and management. He's also a chartered mechanical engineer, member of the Institute of Engineers Australia and a member of the Australian Institute of Company Directors. He's speaking here tonight on behalf of NIM award-winning Zesty Technology. Chris, please share your slides and turn on your camera. Thank you.
Thanks, Alan. Can you see my presentation and hear me? Okay. Is my presentation coming through?
Absolutely, it's perfect.
Yeah.
Yep, we're all good. Okay, hi everyone. Thanks, Alan, for the kind introduction. Yes, I'm joining you from Perth on the west coast of Australia, so sending warm weather your way if you're currently in the middle of winter. It's my pleasure to introduce our company, Calix, and present our Zesty technology to you today. And sincere thanks to the Net Zero Industries mission for the kind invitation. I'll just give you all a moment to digest the disclaimer. Okay, let's get into it. So who are we? Calix, headquartered in Sydney, Australia. We're a dedicated team of industrial research, engineering, and technology development professionals who are dedicated to solving the global challenges in industrial decarbonisation. That's been touched on quite a bit already. We've got a core platform technology that can process raw materials across a range of industries. Our company was founded in 2005, listed on the ASX in Australia in 2018. We've got a highly talented and diverse team totaling approximately 120 employees, speaking 18 different languages, spanning across 5 continents with 9 operational sites in 7 different countries. Today, we've invested about $120 million in the development of our platform technology. So at Calix, we've got a number of different lines of business that utilize the platform technology. In magnesia on the left, we've got commercial operations in Bacchus Marsh and Victoria that have been operating since 2013, producing magnesia-based products such as magnesium hydroxide liquid for water treatment, aquaculture, and wastewater management. In cement and lime, our Lilac business has developed our platform technology to capture unavoidable process CO2 emissions from the processing of cement, meal, and limestone. And in sustainable processing, my area, we're developing the platform technology for new applications in metals and minerals, including lithium and alumina. We've got pilot facilities in Bacchus Marsh that are used to test multiple mineral applications, where we've got a highly experienced team that both operate our commercial and pilot test facilities with on-site, fully equipped material analysis labs and R&D support. Successful testing campaigns have been completed for the electric calcination of alumina and spodumene and the reduction of iron ore with hydrogen, which is the topic of today's talk, which I'll get into now. So Zesty is a novel application of our platform technology utilizing electrical indirect heating and introducing hydrogen for the reduction of iron ore. It's a process that can be easily powered by renewables using no carbon-based fuel and therefore generating no carbon-based emission. You can see in the picture to the right, this is our facility in Bacchus Marsh. It's equipped with solar panels with sufficient capacity to fully power the pilot plant on renewables. Zesty is a fines-based process. It operates at low pressure, non-complex process control. Pre-ground fine materials are introduced into the top of the process and float down through the tube, enabling the process reaction to take place. The hydrogen in this application is introduced into the bottom and moves upwards on its way through. The hydrogen strips the oxygen from the iron ore as it passes in counterflow, and the converted materials exit the base of the tube, and any process emissions or off gas is captured from the top. For Zesty, the product exiting the process is a direct reduced iron that is consumed in downstream steelmaking processes. So what does Zesty offer the iron and steel industry that is unique and different and has the potential to have a significant impact on decarbonisation goals and the challenges we face? So Zesty technology is relevant to the entire steelmaking process and can help to decarbonise multiple processing pathways that can utilise DRI, whether that be blast furnaces, where current papers and research suggest that DRI could potentially be used as an alternative feedstock in the blast furnace, potentially 25 to 40%, as quoted by Midrex, reducing the carbon intensity of existing processes, which are going to be around quite a long time. But also electric arc furnace, where a combination of DRI, pig iron, and scrap can be utilised, noting that the incoming ore type and the quality of the DRI is key here, given the operational tolerances of the EAF, and Jeff explained all of that very well in the previous discussion. The Zesty process is less energy intensive than conventional iron making processes. There's a much lower emissions intensity due to the absence of fossil-based fuels traditionally used for heating and reduction. Key features of Zesty include renewable power, so 100% electrically heated process, no carbon fuels. And this has been proven at our pilot scale facilities in Bacchus Marsh. Fines-based solution compatible with low to mid-grade ores, particularly relevant in Australia, in the Pilbara region, and presents opportunities in other regions globally as well. It's different to a fluidized bed, it's often compared to, but it's not a pressurized system, much shorter residence time, and can easily ramp up and down in a short time frame. The last point, particularly relevant when powered by renewables and the ability to respond to an interruptible grid. There's no requirement to pelletize, avoid significant capital and carbon intensive process steps in the iron making flow sheet. The indirect heating enables hydrogen to be used solely for reduction of iron, no combustion, and therefore it has the potential to achieve minimal theoretical hydrogen consumption in an iron ore reduction process. Further development of the technology at the next scale will introduce a hydrogen recycle and the ability to test that target of minimum hydrogen consumption of 54 kilograms per ton of iron produced. We believe the technology is relatively easily scalable, whereby future commercial plants will consist of multi-tube facilities, allowing for modular expansion, and also flexible given its ability to operate on renewable and interruptible grids. So moving on a bit now to the test results today. What have we achieved so far with our testing? We've completed over 130 tests from 9 different Australian ore sources. You can see from the chart on the right that many of the tests fell within the target range of metallization for DRI feed acceptance into a blast furnace BOF route or a melter such as electric smelting furnace, which has been previously mentioned, is currently under development. In some cases, metallization exceeded 95%. As with all pilot testing, there'll be some outlier results, which you can see on the graph. These are typically associated with the variable process set points in the system, such as temperature, hydrogen flow rates, and of course the incoming properties of the feed materials. It's worth noting that the pilot facility used for the testing to date is not custom built for iron reduction and is a multi-purpose facility that's been retrofitted to pilot the hydrogen reduction of iron ore. We give it the name Batman. It was originally purposed for the processing of battery precursor materials and manganese. Design parameters such as reaction length were fixed, so the reaction zone is quite short in length and therefore residence time is reduced, yet we've still demonstrated some really good results to date. Our proposed demonstration facility, which I'll come on to next, will be custom built, of course. For example, tube length will be dimensioned from the learnings of the feed study work that's been completed to date to maximize residence time in order to further increase metallization and reduction degree results. Other design-specific improvements will also be possible when it comes to material handling, etc. And you can see from the bottom left photograph, we have successfully produced a DRI briquette, so an HBI briquette. We simply took the as-produced reduced iron fines from the pilot facility without making any special additions, such as carbon or binders, and achieved a briquette within touching distance of the industry transportation guidelines with regards to density. Towards FID for a demonstration facility. So our feed study for this demonstration plant concluded in late 2023, supported by grant funding here in Australia from the Australian Renewable Energy Association, ARENA. So the demonstration facility intends to achieve a demonstration of a commercial scale single zesty reactor tube, nameplate design capacity of 30,000 tons, output product DRI. The plant will advance TRL development in terms of process efficiency, power and utilization, process efficiency, power and utilities consumption, and production yield. For example, the facility will include a hydrogen recycle loop to demonstrate minimum hydrogen consumption. Such equipment is simply not practical or economic on smaller pilot scale facilities. And the demo plant will confirm scale-up design parameters for future multi-tube modular facilities. So the demo plant has the objective to produce hydrogen DRI and hot briquetted iron within industry standards, production of a zero emissions product for green iron, demonstrate minimum hydrogen use per ton of HBI, demonstrate ramping and curtailment capabilities, and intermittent and continuous operation. We're targeting FID for the demonstration facility this calendar year. It'll be a 5-year program. Detailed design will be finalized based upon the FEED work already completed, procurement and construction completed within the first 2 years, commissioning and ramp up during year 2 and into year 3, 2-year operational demonstration period with increased campaign duration as we go through the program. So just a bit on the techno-economics. Study works undertaken as part of the FEED study suggested Zesty could produce green HBI at costs close to the range of conventional HBI production before potential carbon penalties are added. Could also reduce emissions intensity of reducing iron ore to metal iron from 1.89 tons of CO2 per ton to near zero. Considerable capital and operating expenditure savings are achievable with the removal of pelletization plants and shaft reduction furnaces or cinder plants from the iron making flow sheet. Low consumption of green hydrogen, approaching theoretical minimum for reduction. It's been discussed that hydrogen pricing is quite expensive. I don't think hydrogen can be avoided in future green iron processing. So if you have a hydrogen-based process, your best bet is to use as little as possible, which this process allows. Moving on to the opportunity for Zesty in both green iron and steel. Just check the time. The versatility of the Calix platform technology allows for it to be considered in a number of process steps for green iron and steel making. The Zesty iron application I've been discussing is a fines-based process utilizing hydrogen for iron ore reduction and renewable electricity for process heating. The output is a green iron product produced without CO2 emission that can be used in downstream BF, BOF routes and EAF routes, depending on the input ore and output product quality of the HBI. We view the Zesty technology as having a whole of industry potential with the adaptability to different ore grades and output DRI quality requirements. The Zesty steel application combines the Zesty iron product with other potential uses of Calix platform technology to produce steel-making products, namely the processing of bio-derived carburants and the production of zero emissions lime, both important additives that are still required for steelmaking applications. And I'd just like to conclude this presentation in touching on scale-up, which is a popular question we're asked. So the Calix platform technology utilizing indirect heating has already been built and demonstrated in other industry sectors. This slide steps you through our scale-up journey in our Lilac cement and lime application. The picture on the left is our Lilac 1 plant, full-scale, single-tube reactor pilot facility. So this will be a similar size, very, very similar looking facility, the tower with the single tube as the proposed Zesty demonstrator. The picture in the middle is the next scale-up demonstration underway, which will be a multi-tube facility with increased capacity. So the individual reactor tubes are not themselves scaled, there's just more of them, with capital savings achieved through common infrastructure, power distribution, and gas handling. On the right, future full-scale facilities demonstrating modular expansion of the previous multi-tube modules. I expect I'm extremely close to time now. So that's the end of my presentation. So thanks so much for your interest and attention.
Thank you so much for that, Chris. We do have 2 questions. You haven't gone much over time. So the first one I want to ask you is, you mentioned the technology's ability to operate with renewable and interruptible power supply. How does that actually work in practice?
Yeah, thanks, Alan. So given the process is essentially a vertical gravity feed process that operates at close to ambient pressure, once the product has exited the bottom of the reaction tube, the electrical heating essentially allows us to rapidly turn down on the power input. So this allows the process to be placed on hold within minutes once the products exit the system. So this becomes pretty critical when managing peak renewable pricing periods that can occur on a daily basis in certain regions. And once those peak periods have passed and power is available from renewable or interruptible grids, we can quickly ramp up again within tens of minutes. So we can be back at temperature through increasing the power input, and then we can just switch the feed back on. So we don't have soak times, there's no refractory inside the tube, and we don't have to reach pressure and stabilize over a long period. So we're really excited to be able to take that further and demonstrate the ability to ramp up and down quickly.
Excellent. And this next question is from our audience, from Ahmed Ali Mansi. I'm not sure if you'll be able to answer it in a very short period of time, but I'll use your discretion, please, and if we need to take it offline, we will. They're working on a hydrogen process for storing and transporting, and they're not sure if it's possible to use electricity to actually heat up big reactors to perform those redox reactions. Have you got some insights on, is it possible? Is this a yes/no answer, or is it a long answer?
There's probably a short and a long one, as there always are. I guess, in terms of our indirect heating, is there is a limitation in the size of a single tube, but we've demonstrated initially on natural gas and now with renewables that we can. The pictures that you saw are sizable facilities, and we can get uniform heating through those facilities with the indirect radiant heat. But I'd be happy to discuss that further with a follow-up contact.
Excellent. Thank you so much for that, Chris. We're moving on now to our next speaker. Again, another technology that has won one of our Netzer Industry Award prizes. From ArcelorMittal, I'd like to introduce, please, Wim van der Sticht. Wim is responsible for technology strategy, decarbonisation, CO2 and circular economy at ArcelorMittal. He has a degree in physics engineering. He went on to get a PhD in semiconductor physics. He joined ArcelorMittal as an operations research specialist, and he's had various roles until he joined the European CTO team to manage the coordination and funding of projects within the ArcelorMittal group. Today, he's responsible for the coordination of the ArcelorMittal climate action initiatives globally, and he is directly involved in innovative pilot and demonstration projects, including Stellanol, Toledo, etc. Please welcome Wim van der Sticht. Your slides are working perfectly.
Yeah, thank you for this very thorough introduction. I'll just jump into it and also try to keep time as well as my predecessors here today. First of all, I would like to give a short introduction to the ArcelorMittal strategy with respect to our objectives to be climate neutral. First of all, you can find most of the details of our strategy in a number of reports that we have published, climate action reports 1 and 2, where an update will follow within this year. It is planned this year to give an update of that, so you will also be able to find more details, even of my presentation, in that report. And also, of course, I want to make you aware that we as a company are already producing also low carbon steel and marketed under the portfolio of the X-Carb product. Very briefly on the ArcelorMittal strategy, which in a sense has not changed since the beginning it was devised. It contains 3 pathways, and I think most of them have already been discussed by the other speakers, so I will be very quickly. You have, of course, the low-hanging fruit pathway, as I call it, the use of more scrap, but it was already mentioned that there is today not enough scrap in the world to produce all steel with that scrap. And also the quality of the scrap is not sufficient to produce all qualities. So also technologies need to be developed to upgrade the scrap to make it usable for all products. Then you have, of course, the pathway switching from blast furnaces to DRI-based steel making, where we could initially start with natural gas and eventually want to switch to using green hydrogen for the reducing agent. But as also mentioned before, the volume of green hydrogen available today is very small compared to what we need for steel production. And additionally, it was also mentioned that to use this pathway, we would need more high quality iron ore than we also have available today. So this is an additional restriction, which makes in the end the conclusion that we also still need to pursue what we call the smart carbon pathway, which is in the end to continue the use of coal, typically in blast furnaces, but to do that in a smart way. And the combination of these different technologies have resulted in our strategy, where we have committed to reduce our global emissions scope 1 and 2 by 25%, and we were even more ambitious in Europe with 35%. So focusing a bit on the smart carbon technologies, so you see it is centered around the continuation of the use of the blast furnaces, which also today are producing most of our fresh steel. And there are a number of initiatives that ArcelorMittal has launched to explore various technologies that can make, let's say, the footprint of a blast furnace much lower than it is today. Going from the re-injection of gases that we produce by top gas recycling, the use of hydrogen in a blast furnace, also to capture emissions, CO2 emissions from our gases and make them available for storage. But today I'm going to discuss 2 other technology pathways a bit more in detail. First of all, our Torero project, where the intention is to replace part of the fossil coal we use in the blast furnace by a sustainable alternative, initially the use of wood. And the second one, which was already highlighted by Andrew earlier, the Stinanol project, where the intention is to capture our carbon emissions and convert them into a useful product. The 2 projects, Torero and Stinanol, are somehow also connected, because on the one hand, Torero, as I indicated, has the objective to convert waste materials, in the first instance waste wood. You see a picture of this typical kind of waste wood, which is really the result of the demolition of old buildings, furniture. So it is really waste wood that cannot be used again to produce another product. So it is not originating from cutting forests or whatever. So it's really a waste product that has no high value use anymore besides being incinerated to produce heat. We are exploring also already alternatives to go even further in the use of waste by also testing or doing tests with SRF, solid refused fuel. So it is really a mix of various types of waste. What we will do with this material, or what we're doing with this material, is in fact to heat it up and to convert it into what we call a biocoal, to introduce the fixed carbon in the product to make it more compatible with coal. Then we grind the material very fine and we mix it with powder coal and inject it into the blast furnace. Then we capture the blast furnace gas, the top gas, we capture it, and then we convert this using biotechnology into chemicals. The total cost of the 2 projects together, investment cost, was 235 million euros, and the total impact that we have expect is to have around 350,000 tons of CO2 per year. And we have started these 2 projects already in 2023. bit more detail on the project, on the technology. So as I indicated, we first inject the waste wood via the form of biocoal into the blast furnace, and then we capture that gas, and we first let the gas undergo a gas treatment. I must say the gas treatment is quite limited. It is really doing some dedusting and removing some very harmful contaminants like cyanides before we send that gas into a bioreactor. In fact, there are 4 bioreactors which are filled with water and also with a microbe, a biocatalyst that is converting the carbon emissions into a chemical. In this particular case, it is ethanol. That technology was developed by the company Lanzatech, and the project Steno is also a collaboration with Primetals and E4Tech. How does this technology work? Well, it is very similar to producing beer or wine. What do I mean by that? The biocatalysts, the microbes, they are in fact very similar to yeasts, and standard yeast that you use for production of wine or beer or whatever, they convert sugar into alcohol, into ethanol. This particular microbe, it converts carbon monoxide, carbon emissions into a chemical, into ethanol. The microbe has been developed in such a way that it maximizes the production of ethanol versus other chemicals. It is not genetically modified, so anybody can find this microbe and use it. But of course, the key to the development is to know how to make this microbe more productive and produce a specific chemical by preference. Once we produce the ethanol, it is in a solution of water, so then we still have to distill out the ethanol to come to a high concentrated solution of ethanol above 99% to be able to market it as a fuel to replace gasoline or as a base chemical to produce various products. The plant itself is very energy efficient because the water is constantly reused, and also the biomass which is produced during the process of the fermentation is then also collected and used in a cogeneration unit to produce heat and power that is again used in the process. So it is very energy efficient. Now, I mentioned we can produce ethanol as a basic fuel, but also as a basic chemical to produce various types of materials. Here are some examples of materials that have been proven to be able to produce from this type of ethanol, going from fabrics to cleaning products, packaging, even running shoes, cosmetics, perfumes, and you see there the nice lady in the Zara dress. So there has already been a collection almost 2 years ago now where fabrics have been produced based on ethanol stemming from a gas fermentation process from steel waste gases. So let's say the options are really very, very large to use this kind of recycled carbon products in various sectors. So now, how have we implemented these technologies? So we have implemented them both at the facility of ArcelorMittal in Ghent. The Torero project was built next to the Sinter plant to use some synergies of waste heat and gas cleaning facilities. The Steno plant was effectively built next to the existing power plant because there was already a pipeline sending superfluous blast furnace gas to the power plant to produce power today. So it was very easy then to make a tie-in to that pipeline to then send some superfluous gas also to the Steno plant. And we have also already constructed or built a ethanol handling and storage facility to be able to ship out all the ethanol via barges and not having to use trucks coming in and out whole day to take off the ethanol. The project was started, or let's say the building of the project was started in 2019. So here you see the surface that was prepared for the plant. Then the construction went on. First, all the steel construction, large construction. Unfortunately, as many, I think we were struck by another virus, the COVID pandemic, that resulted in some delay in the construction of the project. But we try to continue as good as possible, and let's say most of the work was already then done in 21, and this is how the plant looks today, completely finished and in production. And here you see some of the main components of the facility. So you see the two orange pipelines going to the plant. One pipeline is to send in the blast furnace gas, and the returning pipeline is to send back, let's say, the superfluous gas that is not used in the steel and oil plant, that is not consumed, back to the power plant. So we have no direct CO2 emissions from the steel and oil plant itself. You see then the gas handling, as I mentioned, is very basic. So we have a compressor, then we have a pressure swing absorption unit to remove some of the excess CO2 from the gas we send to the bioreactors. Why do we do that? Well, the technology of LanzaTech is working more productive using CO instead of CO2. If we add a bit more hydrogen, we can also convert more CO2 to ethanol, but today we are just using the carbon monoxide as the main input. There are 4 bioreactors, so these are the main or the core of the technology where the magic happens and the carbon emissions are converted to ethanol. And then on the left-hand side, my left-hand side, you see then the distillation unit where we then retrieve the ethanol from the solution itself. And as I indicated, the plant is very energy efficient. So we have a significant process water treatment facility to recover, let's say, some of the main elements which are in the effluent of the bioreactors, and also the biomass which is also produced during the process. And this we send then to the large digester to produce then biogas that is then used in a cogeneration unit to produce heat and power. The milestones we have achieved with this project, so we have produced our first ethanol in 23, and then we have done our first large-scale production in the end of 23, really first industrial production. And then in the course of 24, we have produced more and more, and we have then shipped out first with trucks some of our ethanol, where our first customer was a perfume producer. So, as I said, the possibilities are very large of this kind of product. And also we have sent then end of the year already our first barges to the customers. So the production is continuously increasing of this facility. Torero, I can give you a similar story. So we started in 21 with the construction of the plant next to the sinter plant. Also there, the works continued slowly but progressively. And then we were very happy to receive the reactor itself, the rotating drum reactor that is producing or heating up the waste wood to produce the biocoal. It's the largest rotating drum reactor for torrefaction in the world. It was installed then in February, and then the plant was almost completed in July, and this is how the plant looks today, fully operational, where we are still doing test runs and ramp-up runs to go to full production in the course of this year. Here you see the different elements. You see on the left-hand side that we are still doing some basic checking of all the waste wood we receive, because we always have to make sure there are not unexpected components within the waste. And also we have to dry the waste wood before we process it in our reactor, because the waste wood typically can contain up to 30% moisture, and we want to remove it first before we use it in our bioreactor. But we can do this using waste heat from our process. Since the Torero process is fully self-sustaining, we only need to add some natural gas to start up the process, but once it's rotating, we can use the volatiles from the product itself to feed the heating of the reactor itself, so it's fully self-sustaining. Also, the milestones we have achieved, we have also produced our first biocoal in 23. and we have done also our full commissioning of the reactor at the end of 23, and today, as I said, we are still ramping up and doing some optimizations of the reactor itself. As I indicated, ArcelorMittal has explored various technologies, and we have also looked into the carbon capture. I think it was mentioned a few times that carbon capture is a viable option for decarbonizing the steel industry as well. There are still some hurdles which are not all technical, but also economical, and also the availability of storage locations close to the steel operations. But this hasn't stopped ArcelorMittal to explore potential technologies to be combined with the steelmaking process. So in our plant in Dunkirk, we have done some tests within the frame of the 3D project, European sponsored project, where we wanted to test amine-based technology and to see how effective this technology is in the combination with blast furnace gas. We have done a similar project as well in Ghent, using the technology from Dow Chemicals. So it's a similar technology, but it is using different types of solvents. And also today we have a project ongoing with Mitsubishi Heavy Industries, also in the facility in Ghent, where we want to test again specific amine-based carbon capture technology, but we want to expand the tests not only with blast furnace gas, but also the combination with other process gases like the flue gases of the reheating furnace of a hot strip mill. And then the next stage, we also want to test it with the stack gases from a DRI facility. A very particular aspect of the MHI pilot we have in Ghent is that we have connected also the output of that gas, of that facility, being very pure CO2, with another pilot, which is from the company Decarbon, that is using plasma technology to convert the CO2 back to CO. And this CO could then be a very useful product to either re-inject in a blast furnace as a reducing agent gas, or to use it also as a feedstock, for example, for our Steenol plant in Ghent to produce additional ethanol. So also there we have various options that we can implement to valorize the CO2. We can either store it or we can either reform it to become again a valuable feedstock for various processes. Also there we have achieved some milestones. So this two pilots that have been commissioned and have been started up middle of last year and have been operating until end of last year. So thank you, of course, for your attention, and also open to your questions.
Thank you, Wim. We have run a little bit over time there, and there is one question from the audience that I'll ask you, please, from Anton Fellinger. Can the alcohol distillery be sun-fired through a solar concentrator?
Sorry, can you repeat? Can it be sun-fired?
Sun-fired. I'm sorry, I'm reading the question. I'm not familiar with the term myself, but it seems to be referring to using a solar concentrator as the energy source for the alcohol distillery that we were talking about very early in your presentation.
Mm-hmm. I see the question. Can the alcohol be sun-fired through? So I guess can it be using energy coming from a solar facility?
Possibly, yes.
Yeah, probably it could, but I would say in the current configuration, this is not a necessity to do so, because we have enough waste heat coming from the biomass we produce itself. The most energy that is required in the plant today is to feed the compressor and to feed all the pumps. So for the distillation itself, we do not need that much energy, because the energy or the temperature we are using is only up to around 40 degrees. We do not need a lot of heat to do the distillation step itself. It is in fact a vacuum distillation, meaning that we put a vacuum above the effluent of the steel plant, and we only go to 40 degrees, and we only need that instead of 60 degrees because we put a vacuum on top. The reason for that is that we don't want to kill all the microbes by increasing the temperature to 60 degrees, because these microbes, they live at body temperature, 35 degrees, and if they go to 40, 41 degrees, they get a kind of slight fever, if I can call it like that, but they survive. If you go to 60 degrees, we would kill all these microbes, as we would do with humans, I would say.
Excellent. Thank you so much for that, for Wim. We are running a little bit behind time, so we will now jump to the final presentation of our webinar today. It's my pleasure to introduce you to Jonathan Geifman. Jonathan is the CEO and co-founder of Helios, and of course, another winner of the NIM Awards, sharing details of their technology with us today. Jonathan founded Helios in 2018. Initially, they were focusing on space technology. Don't get excited, Jeff. Over the last 3 years, though, under his leadership, Helios has shifted its focus to green steel technology solutions. Jonathan himself is actually an accomplished entrepreneur with extensive experience in product development, manufacturing, marketing, and distribution across the globe. Please welcome Jonathan Geifman.
Thank you very much, Alan. Can you hear me well?
We can.
Okay. Let me know if you can see my screen.
And we can. Excellent. Thank you.
Okay, brilliant. Okay, thank you very much. As I was just introduced, my name is Jonathan, CEO of Helios. I'll give you a quick introduction to our company, and then we'll dive into the technology, and happy to take any question that you might have later on. So Helios is an Israeli company, and as already mentioned, we started with this wild idea, which is to be able to produce oxygen on the moon. Why to do that? Because apparently humanity is going back to the moon in the coming years, and the most needed consumable there is going to be oxygen to breathe, but mostly to burn propellant. And we learned that if we can produce that oxygen on site rather than sending everything from Earth, we'll be able to save many billions of dollars. Now, given the fact that on the moon there's no plain water and no atmosphere, the most accessible oxygen are the oxides on the ground, pretty similar to here on Earth. But opposed to Earth, there are no typical reducing agents like here, which are carbon, and it's also very hard to access hydrogen. So we define it as how can we produce or reduce these oxides without using Earth-brought consumables. And I have to say that to our great surprise, there is very little research about doing something like this. And this was our starting point almost 7 years ago. We have developed several processes. One of them, the Helios cycle, which I'll elaborate about in a few minutes, was also found to be surprisingly efficient in producing the byproduct metal. So this is something that roughly 4 years ago we have looked into a bit deeper, and we decided to expand our scope of work and focus more on iron making for here on Earth, nothing to do with space. And the reason we decided to go for iron and not other metals, because this technology is applicable to other metals as well, is because it's by far the biggest metal industry on the planet. Literally, humanity is producing 10 times more iron than all of the other metals combined. And also from the sense of carbon emissions, it's a heavy hitter, as everyone here knows. But our initial perception was that the carbon emissions are probably one of the biggest problems in the industry, but we learned that this is actually not the case, at least not for most steel makers. One of the biggest problems is the fact that, and this was mentioned already, that high-grade ores are rarely available in the world, and in order to mitigate this, the mining industry is investing more in beneficiation processes that makes the iron ore more expensive eventually. In addition to pressure from society to decarbonize, there is a major issue in the foreseeable future when it comes to the cost of production. And this is basically where we come to the picture with our novel process. And by novel, I mean this is a process that, as surprising as it might sound, was never looked into before. So what do I mean by never looked into before? So as you can see, the initial reaction in our process is between iron ore to metallic sodium. And this is a reaction that has very little to near zero literature about, and we had to conduct many hundreds of experiments just to fully understand the nature of this reaction and be able to draw the phase diagrams of this reaction, etc. So the idea is to take the iron ore, and apparently this is also quite indifferent to the grade of the ore. So we don't care if this ore has 20% Fe in it or 68% Fe in it. It also doesn't matter if it's hematite, goethite, magnetite, taconite, and so on. The sodium is a pretty potent reducing agent and quite rapidly fully reduce the iron in the ore, and also add that is doing so quite surgically. Meaning when you have your typical silica alumina based minerals, it will not reduce them. So you'll get full reduction of the iron in solid form. So the iron produced is iron powder, then gets briquetted. And sorry, the byproduct is gangue and sodium oxides. Then the sodium oxides are dissociated back into oxygen and sodium with another process that we have developed. The oxygen is pumped out of the system and the sodium is reclaimed back into the system in a closed loop manner. And this is basically the Helios cycle. It's pretty straightforward. Obviously, in reality, it's a bit more complicated than this. This is a pretty high level. But the key advantages is that we fully avoid the use of hydrogen and coal in this process. The energy required is between 3.6 to 4 megawatt hours per ton of iron. And it's also important to mention that this energy consumption includes the production of the reducing agent and almost the whole life cycle of producing that iron. So it's not just the reduction step. Temperatures ranges between 250 to 350 degrees Celsius. And as already mentioned, this technology is applicable to other transition metals like cobalt, copper, nickel, chromium, and more. Can work on laterites and so on. The product is going to be iron. We call it HGI, Helios Green Iron. Basically, this is going to be briquetted iron that contains above 99% metallized iron. And this should be fully compatible both to the EAF and also the BF-BOF routes, making it easier for the industry to take this product as something to be used for steelmaking. This is just, to show a general case for how steel is produced today in the world. There's nothing new here, whether it's via the blast furnace route or DRI route. And what I want to show you is what happens when we use this technology and how it, in a way, optimizes the whole value chain. So once we use our process, we can pretty much skip beneficiation. And this is something that we've tested quite thoroughly with over 50 different samples from literally all continents, maybe besides Antarctica, using run-of-mine directly, using tailings, as mentioned, as low as 20% Fe, and we pretty indifferent to the other minerals and impurities that are in that ore. So it doesn't matter if it has high phosphorus or sulfur, high alumina, and so even humidity, a very large range of particle size, and so on. The sodium will, as already mentioned, quite rapidly fully reduce the iron. and then that iron can basically go straight into steel making. And this process in practice can make the two more energy and carbon intensive steps within the value chain, which are beneficiation and iron making, redundant. It also can improve the transportation step, because if you do this in adjacent to the mine, and I know that this is a concept that has been discussed already, generally speaking, in the industry, to do this near the mine, you can also improve the efficiency of transportation and shipping as well, because you ship iron and not dead mass. Just to quickly sum up the key technological advantages, as we see it, the biggest advantage is the fact that we can use low grades. We can use tailings, and this is also one of the more significant factors to reduce the overall OPEX of this process. We do not require hydrogen, so we're not going to be tied to the bottlenecks of hydrogen consumption and production and cost. Direct emissions are reduced to zero, and we do estimate that for the full life cycle of the iron production, from a cradle to gate, we're going to use less energy than any alternative technology as far as we know. Also, another interesting advantage is that the kinetics of this process are exceptionally fast, meaning we can basically produce more iron in a smaller volume. So imagine that, for instance, today we are producing in the lab kilograms and tens of kilograms of this product. The first small demonstrator we're going to build will produce in the capacity of 1,000 tons or a bit more per year. And that machine is going to be fairly small, like half the size of a 20-feet container. And the larger scale would be using two 40-feet containers to produce in the ballpark of 50 to 60,000 tons a year. That has some interesting advantages, because basically it allows us to start faster. You know, we're thinking about how fast can this be commercialized, then we can start faster, building smaller units that can be deployed and mobilized and deployed in various places, like in proximity to the mines, and so on. And in the future, this can give great operational flexibility and overall reduction of OPEX. And in regards to OPEX, we also estimate that we're going to reduce it on average by roughly 30% if we compare it to pig iron in the world, and also accounting for the carbon in the product. And the key driver for this is because we can use the low grades, the run-of-mine and the tailings, in order to produce the iron. And lastly, and this is especially mentioned because sodium is the material that is in a way unfamiliar in this industry, and there's some worries about whether it is safe or not. But we've been dealing with this for several years now, and we learned that this is actually safer in many ways than how iron is produced today in the world, because we do not deal with hazardous materials like carbon monoxide or hydrogen. Actually, the greatest risk with sodium is that it produces hydrogen in small amounts when coming in contact with water. But I'll also say that this is mitigatable quite easily. We've been testing ores that has high humidity level in them, and we can even gain some heat from that interaction if managed properly. So this is not something that we see as a great challenge. It's very easy to store it, to handle it, to ship it, in opposed to other reducing agents. So, one second. Okay, this is my last slide, and it's something that we have realized that in a way has very unique feature to this process. And what you see here basically is how much energy is required in order to produce 1 ton of iron with different ore grades. So on the far left, if we use 67% high-grade ore, and by the way, we don't care if it's pellets fines, lump, tens of microns or 10 millimeters per particle, then we will need roughly 3.6 megawatt hours per ton. And on the far right, if we use 34% iron in the ore, we'll need roughly 3.7 megawatt hours per ton. Now, this is counterintuitive because one would assume that using 34% means we'll need roughly twice the mass of the ore in order to produce the same amount of iron, but the effect on the energy consumption is minuscule. The reason for this is because almost all of the energy, actually over 96-97% of the energy in this process goes into the reproduction of the sodium. So, and that because the sodium surgically reduces only the iron, it means that the amount of sodium oxide we need to break apart again directly correlated to the amount of absolute iron in the ore. So it doesn't matter the grade. There's a trade-off, of course, when we need to deal with more gangue to be separated, but that does not affect the energy consumption as the amount of sodium oxide to be dissociated. As far as we know, this is the only process that bears this interesting feature and what allows us to gain a competitive advantage when working with lower grades than other technologies. That's it. Thank you very much.
Excellent. Thank you for that, Jonathan. 2 quick questions for you, please. The title of the presentation was specifically about or rather avoiding those green premiums. So what are those main factors that enable Helios to avoid green premium charges?
Sure. And I'll start with a comment about this, because when we approach this, and we're not from the industry originally, we were seeing green premium as something that will limit our ability to actually penetrate the market. So when approaching this, we were thinking, okay, so if we want this technology to truly take off, we need to avoid green premiums. And more than that, most likely we'll need to, even cost parity might not be enough. Like historically, if we look at the steel industry, technologies that quickly took off are technologies that made steel cheaper than how it was produced before. And the ability to make it green, this is like the cherry on the top. And we need to do this without relying on external incentives, credits, or anything like this. And to your question, the key contributor to being able to do this without green premium is obviously significantly reducing the OPEX. And this can be done by working with the lower grade ores, optimizing the value chain in the sense of, avoid a significant part of beneficiation, better using the transportation by sending a product that is 99% plus metallized Fe, and also by using a product that has a tiny slag content in it, significantly increase the value in use for the steel makers. Lastly, the fact that we recycle the reducing agent within our system is also a significant contributor to that.
Excellent. Thank you for the clarification. Now, apologies given I'm not a chemist, and I know Jeff Brooks has actually put a number of references there in terms of sodium chemistry in the chat, but there is a question, in case it hasn't been answered. How do you differentiate the sodium metal reaction from other impurities rather than iron oxide? And can that actually decrease the reaction efficiency?
Do you mean, just making sure I understand the question? So if we use low grades that has other minerals, than just iron oxide, how does the sodium does not reduce them? That's what you mean?
I'm afraid I'm reading someone else's question. It says, how do you differentiate sodium metal reaction with other impurities rather than with iron oxide?
Okay, so basically, sodium thermodynamically will reduce only the iron in a typical iron ore. So alumina and silica-based materials will not be reduced. There is a diagram in chemistry, it's called the Ellingham diagram, and there you have like a ranking of what metal will reduce what metal. And the lower you are, then you'll reduce all the metals above you. Obviously, it depends on pressure and temperatures and stuff like that. But you can see that the sodium is below iron, but is above silica and alumina, for instance. So it will not reduce the silica and alumina, and it will reduce the iron. If we have ore that has nickel oxide in it or copper oxide in it, it will reduce it. But this is, in most cases, not a typical ore body that's being used in the industry. And in your typical case, when your bulk constituent, other non-ferrous constituents are silica and alumina based, and this is okay. Same goes with phosphorus. We see great advantage there that we can pretty clearly fully strip the phosphorus from the iron. So we have, for example, tested and ran a whole series of tests on high phos ore that has like in the ballpark of 0.2% phosphorus in it, and managed to fully strip the phosphorus in one go, meaning just in this process.
Excellent.
I hope that answered. Yeah.
I can almost sense that Professor Brooks would love to have a conversation that we'll probably need to take offline. But with that, I thank every one of our speakers for their detailed presentations and sharing with us today. If I can call out, Thomas has put into our chat and our Q&A a survey or poll that we would appreciate people to give us feedback on how they'd like us to steer this webinar program in the future, how it can be better suited to our audience to actually give them greater benefits. What I'd also like to call your attention to is our website. That link will be put into the chat and sent on email to all participants afterwards, where we share not only copies of the slides of these webinars, but also links to our YouTube channel where you can look at past webinars that have been held, and of course look at and hopefully follow on our LinkedIn channel, where we actually share upcoming events, publications, and a whole range of partner activities from the international industrial decarbonisation community. So with that, again, thank you so much to all of you for attending. A very special thank you to all of our presenters for giving up their time and sharing their knowledge with us all here tonight. And I thank you for joining us, and I look forward to welcoming you to the next upcoming webinar in our series, which will be advertised, as I said, on our website and LinkedIn in the coming weeks. Thank you, and from here in Australia, a very good and quite late good night.